In this last video of the series, we will talk about countable sets. A set S is countable if there exists a bijection f from the natural numbers to S, and since it is a bijection, its inverse exists, so it is the same as if saying that we have a bijection f from S to the natural numbers. It means that we can list all the elements of S by S equals the elements S1, S2, and so on. So necessarily, if a set S is countable, then it must be an infinite set. Let's look at the first proposition. Suppose we have a subset of natural numbers, say S, which is infinite, then S is countable. To prove this, we define a function f from the natural numbers to S inductively as follows. F of 1 is defined to be the minimum element of S. We know that S has a minimum element because it is a subset of the natural numbers, and the minimum element of the natural numbers is 1. For n greater than or equal to 2, f of n is defined to be the minimum of the set S taking away f of 1, f of 2, up to f of n minus 1. So f of n is the minimum element of S except the elements which are some values of f. Note that f of 1 is less than f of 2, is less than f of 3, and so on, where f of n minus 1 is less than f of n in general, so f is injective. Assume for a contradiction that f is not surjective. Then there exists a smallest element, little s, in the set S taking away the image of f. If little s is the minimum element of S, then little s is f of 1, which is in the image of f, and this is a contradiction. So there exists an element in S which is smaller than little s. Let little s prime be an element of S, be the largest such element. Since little s is the smallest element not in the image of f, we must have that little s prime is in the image of f. So there exists a positive integer m such that s prime is f of m. Now f of m plus 1 is greater than f of m, which is little s prime. This implies that f of m plus 1 is greater than or equal to little s. Let's call this star. If f of m plus 1 is greater than little s, then little s is the minimum element of S taking away f of 1, f of 2, up to f of m. That means that little s is f of m plus 1, which is a contradiction. So star implies that little s equals f of m plus 1, which is in the image of f. Again, a contradiction. This shows that f is surjective, and this completes the proof. The second proposition asserts that the integers and the rational numbers are countable sets. Let's first prove that the set of integers is a countable set. We define a function f from the natural numbers to the integers by f of n equals n over 2 if n is even, and negative n minus 1 over 2 if n is odd. This means that the image of f can be listed as the set 0, 1, negative 1, 2, negative 2, and so on. This is clearly the set of integers. It is easy to check that f is bijective, which implies that the set of integers is countable. For the rational numbers, let's consider the positive ones, which is the set of elements of the form m over n, which are rational numbers and are positive. We define a set S of elements of the form 2 to the m times 3 to the n, where m and n are positive integers. Note that S is a subset of the positive integers. We also define a function f from the positive rational numbers to S by f of m over n equals 2 to the m times 3 to the n. We can easily check that f is bijective. Since S is a subset of the positive integers, and S is infinite, by the first proposition, S is a countable set, so there exists a bijection, G, from S to the positive integers. Now G composed f is a function from the positive rational numbers to the positive integers, where f and g are both bijective. So G composed f is also bijective, which implies that the positive rational numbers is countable. So we can list the elements of the positive rational numbers as Q1, Q2, Q3, and so on. Hence, the elements of rational numbers can be listed as 0, Q1, negative Q1, Q2, negative Q2, Q3, negative Q3, and so on. So the rational numbers is countable. The third proposition states that the set of real numbers is not countable. To prove this, let's suppose for a contradiction that the real numbers is countable. Then we can list all the elements of the real numbers as follows: x1, which equals a1, point a11, a12, a13, and so on; x2, which equals a2, point a21, a22, a23, and so on, where a general element is of the form xn, which equals an, point an1, an2, an3, and so on, where ai is an integer and aij is an element from the set 0, 1, 2 up to 9. Now we can produce a number which is not in the list. To do so, pick an integer b1 such that b1 is not equal to a1, c1 an integer from 0 to 8 such that c1 is not equal to a21, c2 an integer from 0 to 8 such that c2 is not equal to a32, and so on, where we continue to pick cn, an integer from 0 to 8 such that cn is not equal to an plus 1 n. Now let x be the real number b1, point c1, c2, up to cn, and so on. Then x is not in the list, because for any xn in the list, there is at least one digit, namely an plus 1 n, different from x, namely cn. And the proof is complete.